Joining us today to this Carbon Eye webinar. In this webinar, we will be providing some information about Carbon Eye. This is a NASA Earth System Explorer mission concept for greenhouse gas observations. Again, for folks that are just joining, we will be recording this webinar. So what we'll be covering today, we're going to have two presentations. The first from Anna Mikulak, who's our deputy PI, on the Carbon Eye science needs and the decadal survey. And Christian Frankenberg will also be presenting our principal investigator, the mission science objectives and the technical approach. We will also be having a Q&A session towards the end using Mentimeter. So you might wonder, what is Mentimeter? I have a slide that describes how we plan to use this. So you can scan the QR code or go to menti.com and enter this code. You can enter questions, upvote questions, and that just allows me to see the questions, and then we'll be feeding them to Anna and Christian during the Q&A. So we wanted to just give you a sense for the folks that have registered in terms of their distribution. We've got on the left here a representation of the distribution of our participants from academic institutions that are sort of dominating, in addition to government and research organizations, but we do have some private sector and nonprofit participation, and obviously there's a number of folks that we couldn't ascertain organizations. Similarly, we've got nice representation across the globe, dominance from the United States, but folks from Germany, India, Canada, Japan, and a number of other countries that are listed here. Great. So I want to introduce our two speakers. Christian Frankenberg is a professor of environmental science and engineering at the California Institute of Technology. Christian has 2 decades of experience in global carbon cycle studies and is an expert in remote sensing of atmospheric trace gases, in particular methane, carbon monoxide, and carbon dioxide. And his main research focus is the global carbon cycle and how to connect models with remote sensing data, both for the atmosphere as well as the surface. Anna Mikulak is the founding director of the Climate and Resilience Hub at the Carnegie Institute for Science and is a professor in the Stanford Doerr School of Sustainability. Anna has been developing methods that leverage atmospheric observations of greenhouse gases for characterizing both anthropogenic emissions and nature-based carbon sinks for 2 decades. Her main interests focus on making greenhouse gas information actionable for managing emissions and for anticipating climate adaptation needs. And with that, I'm going to hand it over to Dr. Anna Mikulak.
Thank you, Andrew, and thank you everyone for joining us this morning or this afternoon, depending on where you are. I see we already have over 200 people signed in, which is wonderful. Given the broad range of disciplines and interests that the audience today is coming from, what we wanted to do is to start with a relatively high-level overview of the science behind Carbon Eye and the need for the Carbon Eye mission. And then Christian will go into some details on Carbon Eye itself. Given that this is the first webinar, we will be staying at a relatively high level, but we're very happy to either answer more detailed questions in Mentimeter, and also we plan to have additional webinars that go into more detail. And so, as most of you are likely aware, our planet is warming. What you see here on the left-hand side is a plot from the IPCC AR6 synthesis report showing temperatures at the global level from 1850 all the way up to 2020. And what you can see is that even back in 2020, we were approaching a 1.5 degrees centigrade warming. What you see on the right-hand side is what has been causing this warming. And so you see the observed warming in the first orange bar here, and you can see that essentially all of that observed warming is attributable to human influence, primarily through emissions of greenhouse gases. Of course, there are several different greenhouse gases, but the 3 main anthropogenic greenhouse gases that have been causing this warming are carbon dioxide or CO2, methane or CH4, and nitrous oxide or N2O. And what you see in these small plots from the IPCC here are very broad estimates of increases in their concentrations globally since the start of the industrial era. What you can see then on this last plot is current emissions of these greenhouse gases. So CO2 emissions from fossil fuels, CO2 emissions from land use and land use change, and then non-CO2 emissions. And so really what you can see here is that CO2 is the main gas contributing to global warming, but methane is second in line. The question is, where is all this carbon coming from and where is it ending up? On very large timescales, we actually know the answer to this question quite well. In terms of the size of the reservoir for carbon, we have geologic carbon, carbon in the oceans, carbon in plants and soils, and carbon in the atmosphere. And you can see the size of these reservoirs prior to the start of the industrial era. Over the last 150 to 200 years, we have extracted a lot of carbon, both from geologic pools, in other words, fossil fuel, as well as from plants and soils through land use change. And the systems on the planet have reacted by actually taking up part of this carbon that we have emitted and putting it back into plants and soils and back into oceanic carbon. So on this very large timescale, we actually do know what is happening. However, what we're interested in now is understanding the system on much finer timescales so that we can have actionable information for managing the Earth system. What I'm showing on this slide are more recent histories of concentrations of, on the left, CO2 and on the right, methane, as measured by NOAA, the National Oceanic and Atmospheric Administration. You can see, for example, for CO2, this relentless rise year over year in the black line, in that every single year, CO2 concentrations are higher than the year prior. What you see in red is the seasonal cycle going from the Northern Hemisphere summer to the Northern Hemisphere winter. On the right-hand side, you see the same plot for methane, and generally it's a similar story, but you'll notice, for example, this leveling off of concentrations that restart of this rapid rise in methane. And one of the interesting things is that even at this global scale, we don't really fully understand what has caused this plateauing and then further rise in methane concentrations. As a result of a lot of science and analysis that have been done, including looking at isotopic signatures, we think this is more due to microbial sources rather than fossil fuel type sources and natural gas sources, but this is still an area of active research. If you dig down a little bit beyond this global view and try to understand where is all, in this case, methane coming from and where is it ending up, you see that there are main components in orange, which are the anthropogenic components, in green, which are the natural system components. But really what I want to draw your eye to is, for example, if you look at wetlands and inland freshwaters, if you look at the numbers in parentheses, we have essentially a 100% uncertainty in our understanding, even at the global scale, and even averaged over a full decade, as to what the emissions associated with wetlands and inland freshwaters are. And even when you look at total emissions, when you compare top-down methods that use atmospheric observations to bottom-up methods that attempt to scale up our process-based understanding of what's driving methane emissions, you see a large discrepancy between those estimates. So there's a huge scientific gap, as well as a gap in our ability to inform action that needs to be remediated. The same is true for CO2. So again, here you see best estimates of average emissions and uptake across a full decade. And for some components of the CO2 budget, whether it be for fossil fuel emissions, for emissions associated with land use change, or uptake associated with plants and soils, you see that in some cases the uncertainty is on the order of 50% of the total number. And if we add up our best estimates of all of these components, we end up with a budget imbalance, even on decadal scales, of over a gigaton of CO2 per year. Now, next you might ask, well, why is this problem so difficult? Why haven't we solved this problem already? The analogy I want to draw your attention to is a cup of coffee. And so think of greenhouse gases as cream and think of the coffee as the atmosphere. And so we are essentially injecting greenhouse gases into the atmosphere. And in the atmosphere, those greenhouse gases are getting mixed. So we refer to that injection of greenhouse gases as a flux. And the concentrations of the cream or of the greenhouse gases is what we can often measure from atmospheric observations, whether they're in situ or space-based. And so in a lot of ways, essentially what we're trying to do is we are taking this creamy cup of coffee, this atmosphere with greenhouse gases in it, and trying to extract back out how much cream did we pour into this cup and where was it poured and when was it poured and how quickly was it poured. This is conceptually the problem that we're trying to solve. If you want to look at it more from a carbon dioxide perspective rather than a coffee perspective, this is a model simulation from NASA Goddard showing us what we think atmospheric concentrations of CO2 look like. If you squint, you can see outlines of North America here, South America, Africa, and Europe. And what you see are these streaks of carbon dioxide emanating from locations with large emissions. In this case, we're looking at the Northern Hemisphere winter. So not only do we have fossil fuel emissions, but we also have respiration from plants and soils. And so this is the analogy in our science space of the coffee cup I showed previously. And what we're trying to do is to untangle all of these concentration variations to then infer back what we call the fluxes, so the emissions and the uptake of greenhouse gases at the Earth's surface. If we had this picture everywhere all the time, the problem would be challenging, but doable, because you can actually see all of the streaks and you can imagine untangling these streaks to get at the fluxes. However, this is just a model simulation. We can't actually measure this everywhere all the time. Instead, what we have is an expanding network of in situ observations from individual towers or airborne observations, but also increasingly missions that attempt to measure greenhouse gas concentrations from space. What I'm showing here on the left are either planned or existing or historical missions in the CO2 space, and on the right, planned or existing or historical missions in the methane space. And at first glance, this looks like a lot. It might seem like we actually have many, many satellites measuring these greenhouse gases. But if I black out those missions that are not actually currently flying, and also those missions that don't offer public access to their data, what you notice is that the picture gets a lot sparser. And so in terms of global mapping of CO2 and methane, we are left with a very small number of missions, OCO2, OCO3, which I know many of you know about, GOSAT, GOSAT-2 from our Japanese colleagues, and a similarly small number on the methane side. And then we have another small number of satellites that focus more on point sources and point emissions. So they don't allow you to have a global view, but they might allow you to have very fine spatial resolution at individual locations. To give you an idea of what this looks like, what I have here is an animation of CO2 concentrations as measured by the OCO2 and the OCO3 satellite mission. And so if you mentally compare this video to the video I showed just 2 slides ago, you can see that we are nowhere near having that full view of greenhouse gas concentrations everywhere all the time. And so if you think back to the coffee cup analogy, imagine instead of seeing the full cup of coffee, we are just seeing individual pixels at different places and times, and still trying to infer exactly where did all the cream come from and where was it injected. I'll say 2 more things about this slide. The first is, while these streaks of information look relatively wide for the purposes of this video, in reality, the swath width of OCO2 is on the order of 10 kilometers. So each of these stripes is really just 10 kilometers wide of information. And the second thing that I'll mention, just because I know that Christian will allude to this a little bit later on, is even for these streaks, notice how they tend to disappear in the Amazon, and in other tropical regions around the world. And this is because these regions tend to be very cloudy, which makes it very difficult for these existing missions to sample there. And that's something that I know that Christian will talk about a little bit more when he is showing his slides. Lastly, just before I hand things off to Christian, I want to orient everyone as to where this mission fits within the NASA portfolio. So the decadal survey for Earth observations from space was completed in 2017, published in early 2018. It's entitled Thriving on Our Changing Planet. And one of the new recommended and existing program elements that came out of this report were these Earth System Explorer missions that Andrew alluded to already. These missions, as you can see here, seek to address one of 7 prescribed target observables with medium-sized cost cap missions under $350 million US. And the original plan was to have 3 competitive cycles within the decade. The purpose of these was to address key science and application needs, and the 7 target observables were not prioritized by importance. Instead, competition was expected to drive innovation. You can see on this slide the 7 observables that were part of that Earth Science Explorer program with greenhouse gases at the top of this list. Again, these are not prioritized. Many teams proposed to this program, and on May 7th last year, NASA selected 4 missions. These 4 missions were CarbonEye, Odyssey, Strive, and Edge. I have highlighted here in red the observables that those missions targeted. These 4 missions will then be down selected to 2 final missions near the end of this year. And currently these 4 missions are undergoing deeper analysis and deeper study, which is what Christian will speak to present to NASA the most compelling case for why each of these missions should be among the 2 that ultimately fly. And with that, I will hand things off to Christian, who will tell you a little bit more about CarbonEye itself and what we think we can do with this mission.
Thank you so much. I hope you can hear me well. If not, one of the Andrew or Anna should chime in and let me know. So it's my pleasure to take over now. And thanks so much, Anna, for giving this introduction. So I will go a little bit more into the details of CarbonEye right now. Oh, somehow this is not moving. So I'm using this example slide here at the beginning to just set the stage, because over the past year, the devastating LA fires really took a personal toll on our communities, including JPL, and it underscored the need to understand fires in the Earth system. Even before these events, CarbonEye, our team focused on fire emissions, but now seeing the direct impact made it kind of personal. And the image on the right shows a key benefit of the shortwave infrared measurements that we are basically employing here. That is, aerosols from fires that we see on the left side in the visible image from the Palisades fire, they become practically invisible in the shortwave infrared, letting us see through the smoke to measure carbon-bearing gases directly. And this capability turns out to be crucial for capturing accurate fire emissions, which is one of our CarbonEye goals. Sorry, technical difficulties with how to proceed in the slides. Our CarbonEye mission, going back to the basics here, has 3 core science objectives. First, we want to identify methane, CO2, and CO emissions hotspots worldwide. And these local detections will directly feed into a global inversion system that allows us to quantify monthly fluxes of these gases at spatial scales from 12 to 100 kilometers. Finally, by fulfilling these goals, we can really attribute and quantify the processes driving both natural and anthropogenic emissions. In practical terms, we will cover everything from point source detection that you see on the left side there, to regional scale inversions that capture fine-grained variations across like 100-kilometer domains, and ultimately continental scale fluxes like in the Amazon basin. At smaller scales, plumes and gradients are sharper, whereas on the continental scale, local variations blend into these mellower patterns. And this is similar to what Anna just showed of the snapshot of milk being poured into the coffee. If you really take a high resolution image when the flux starts of the milk into the coffee, you really know where it was being emitted into. And if you would watch a coffee cup with like 4-pixel resolution, you really wouldn't know where you started with. So the more detail you see in these swirling patterns, the higher your spatial resolution is. And our mission basically balances those needs. We need point source detection through regional inversions all the way up to local large-scale budgets. Now I'll discuss the trade-off between sensitivity and spatial resolution a bit later. When designing a new NASA mission, we always have to carefully look at the existing and upcoming instruments that measure greenhouse gases, not just US missions, but global efforts as well, and identify what gaps remain. It relates to like Anna's plot about all the different missions that measure greenhouse gases. In NASA speak, we sometimes refer to this as finding the undiscovered country of our knowledge. Right now, the biggest shortfall that we have is really the lack of data in the humid tropics, largely due to the poor spatial resolution of many dedicated greenhouse gas instruments. They typically have kilometer scale footprints and they can't see through these popcorn clouds that are very prevalent in the tropics, where the gaps are really smaller than a kilometer, leaving large fractions of the tropics unmeasured. And if we can't observe the tropics, we really can't fully understand global carbon cycles. And this reality has become a driving requirement for CarbonEye, which is explicitly optimized to basically obtain high-resolution greenhouse gas measurements, even in those cloudy regions, because this is really something that no current mission and no planned future mission can really achieve with the accuracy and precision that we do. One concrete example of this is basically a consequence of what Anna has shown before. This is an image showing the data yield of OCO2 in the humid tropics. While OCO2 doesn't measure methane, it stands out as kind of the highest resolution dedicated CO2 satellite thus far. Still, in the humid tropics, particularly over the Amazon and Congo basin, we have data yields that are below 0.5%. And practically speaking, for every 200 tropical measurements, fewer than one is usable. That's pretty bad, and especially it dips even further in the wet season, just when methane emissions from wetlands are the strongest. That means that our understanding of seasonal methane or carbon fluxes in general, which is crucial for grasping the global carbon cycle, remains limited because we simply lack cloud-free observations in these critical ecosystems. You might wonder whether it really matters that we are missing the humid tropics. Yes, it absolutely does, because these are precisely the regions where we find the largest magnitudes of methane flux and uncertainties. And this is from a recent paper that was published this year. In other words, the places we measure the least are also the most important for understanding how methane is changing globally, or the carbon cycle in general. It's no surprise that the global methane budget remains contentious. And we can't firmly observe wetland emissions in the tropics. It's really tough to resolve whether rising methane comes mostly from natural wetland feedback or from agricultural or waste sources. It's basically one of the key motivations behind improving satellite coverage over these poorly unobserved but critical areas. So the bottom line is basically, without the tropics, we don't understand the global carbon cycle. And the question now is, how do we design an instrument that basically fixes these gaps? To tackle this issue, we rely on solar absorption spectroscopy and the 2 to 2.4 micron spectral range, which lets us detect enhancements right near the surface, something that thermal infrared sensors would struggle to do because they don't have sensitivity towards these layers in the atmosphere. The bonus is that we have both CO2 and methane strong absorption features in that band, and there's also room to measure CO at the long wavelength edge. This one-band approach allows not only high precision retrievals for each gas, but also supports chemical fingerprinting. By measuring multiple gases together, we can distinguish, say, wetland emissions from industrial sources, since different processes yield different CO2 to methane to CO ratios. The challenge is how to design the instrument so that we can see through those popcorn clouds in the tropics without sacrificing our point source detection or missing larger area fluxes that are important. And the next slides will just walk you through the trade-offs that we made to optimize for those challenges. Okay, what this figure illustrates, focusing on the orange line, please, is how the effective revisit time in the tropics changes depending on ground pixel size, assuming we can only have so many cross-track detector elements, which is usually a constraint for designing any satellite mission. The surprising takeaway here is that you end up with a shorter effective revisit time, which is good, by using smaller pixels, about under 500 meters, even if you're not scanning every day. In other words, measuring fewer times at high spatial resolution can really yield more usable cloud-free data in the tropics than measuring more often at coarser resolution. which might be counterintuitive. But that really what defines the mission requirement for CarbonEye, opting for monthly global coverage at fine resolution rather than daily coverage that can't see through the popcorn clouds and basically getting no data at all in time. So we find that optimal space in terms of spatial resolution to be below 500 meters in the tropics. Measuring at these fine spatial resolution, however, introduces a new challenge. We have fewer photons that land in each pixel, detector pixels, and that reduces the signal to noise ratio. And we are not shot noise limited anymore. That is a problem. That leads to a spectral trade-off. So if we push for high spectral resolution in the 2-micron band, it lowers our SNR, especially over darker tropical surfaces. Whereas coarser spectral resolution could brighten our signal, but it also blurs the atmospheric features that risk us merging different molecular absorption lines, or basically having like error correlations between methane or CO2 with water abundances and the like. So after running some design studies, we found a sweet spot for our CarbonEye instrument. It's the middle ground spectral sampling that's fine enough to distinguish methane, CO2, CU, and N2O absorptions, but broad enough to gather enough photons for having a good, robust SNR at these small pixel sizes. In other words, here again, going at any finer end resolution would shrink our bandwidth, limiting the total number of methane lines we capture and ironically reducing overall precision. Going too coarse would boost SNR but hamper our ability to separate all these different trace gases or manage surface interference. And our final solution is basically a balance between these constraints, ensuring that we can measure all the relevant gases in a single band while preserving good retrieval performance. Again, yay, we are close to the optimum. We are a little bit to the right-hand side to the coarser resolution because we want to get CO2 and CO in there as well, which are basically on the two opposite ends of our spectrum. Last but not least, overpass time is always a problem. And since clouds follow a diurnal cycle with increased convection in the afternoon, optimizing the overpass time is also crucial, yet challenging when relying on cloud statistics alone, because most of the high-resolution cloud statistics is only taken at 1 or 2 times a day. However, we are lucky that we could use OCO3 data, which is on the ISS, which is not a sun-synchronous orbit, and we can observe the data yield from OCO3 at different times of day. And we found in the red line to focus on here that between 11 and 11:30 local time is optimal. This window is early enough to avoid most convective cloud system while still being close to noon, ensuring that we have a favorable solar angle for retrievals. So yay, this is kind of our choice for the optimal local overpass time. But now I'll dive into some of the specific implementation of how CarbonEye will operate. Let's first look at the dominant measurement mode that will measure basically most of the time. It's the global mode. And this mode is really designed to provide full coverage of the Earth land surface with a revisit time of approximately 28 days. It follows a typical sun-synchronous nadir mapping approach with a swath that's slightly over 100 kilometers, enabling comprehensive land coverage while also downlinking some data for all near coastal regions. And if we find something funny in these areas, we can actually activate glint mode to follow up on unexpected findings, which boosts the signal level. On the left, you can see an illustration of CarbonEye's daily orbit passes over like multiple days in the life of CarbonEye. And in global mode, the instrument achieves a spatial resolution of around 300 meters. During each exposure, the satellite ground track basically shifts by 300 meters along track, and we use 8 to 10 pixels per measurement to enhance the signal to noise ratio and get the good measurements that we need. The second measurement mode that is key is the target mode, which allows us to really focus on a select set of high priority areas, up to 25 in total, with much finer spatial resolution. This is achieved through image motion compensation, where we tip and tilt the satellite to reduce the ground speed of the slit projection on the ground by about a factor 10. As a result, we can achieve pixel sizes of approximately 35 meters while covering regions up to 100 by 100 kilometers. For those in the know, this is the LA basin on the left in the simulations and also on the image shown below. In this mode, we can observe up to 3 targets per day with the potential for weekly revisits at some locations. This helps address a key limitation of the global mode, where each location is only observed every 28 days due to the 100-kilometer swath width. The target mode is really designed to provide a refined and high-resolution view of critical areas that drive the global and methane carbon budget, allowing us to gain an even more process-based understanding than what is possible with the global mode. Okay, sorry, I have to go back. So what might CarbonEye observe? you might wonder. Here I'm showing a high-resolution model run from ECMWF, simulating methane variations across the Amazon basin at about 10 to 12 kilometer resolution. In this case, you see strong methane enhancements near the Amazon River, primarily due to wetland emissions, as represented in the specific emission inventory that ECMWF used. And the model predicts methane gradients on the order of 2.5% if we would have this artificial orbit of carbon eye going through there, which with carbon eye swath would correspond to variations of approximately 50 ppb. And our key objective is to achieve measurement uncertainties in the range of 0.25 to 0.5%, that is 5 to 10 ppb over these spatial scales of 12 kilometers. The level of precision would allow us to resolve these methane gradients very finely across these regions. However, the current space-based observations do not provide enough cloud-free data along such a track to effectively capture and validate these variations. And another advantage of carbon eye is the ability to simultaneously measure multiple trace gases. And in this Amazon example, a zoomed-in view of these trace gases to the right for methane, carbon dioxide, and carbon monoxide reveal that we have minimal covariations between them. There's some covariations between due to incomplete combustion, but the wetland methane emissions are largely decoupled from CO and CO2 sources. So this separation on top of the spatial separation really allows us to extract more process-based insight into regional methane dynamics. So why and how can we still measure in these areas? If we zoom into these areas and would have a hypothetical carbon eye data in the middle with 300-meter resolution, which is the global mode, or the fine resolution mode at 50 on the left, you really see that we can fully resolve popcorn clouds. And that also enables us to have enough cloud-free measurements in between that we can aggregate to the model inversion grid scale of about 12 kilometers to basically run these inversions. While if we had only 7-kilometer resolution, which is kind of currently state-of-the-art for many satellite measurements, we would not get a single measurement at all, because in all of these grid boxes, there would be a subpixel cloud, which usually basically makes the retrieval unusable. So this is basically where we are. The next example is even more extreme. This is Asia, where a lot of methane emissions are happening that are significantly higher and more spatially variable than in the Amazon basin. And here we have fluxes that are not only stronger, but also more localized, leading to methane gradients that are on the order of 5% or over 100 ppb. So these are well within our detection capabilities, and we will see fine-grained resolutions of those. However, the real challenge in this region is source attribution. So many emissions might originate from overlapping sources that could include agriculture, combustion, or waste in urban environments. And our carbon eye high spatial resolution really allows us to pinpoint emission sources at much finer scales and helping to disentangle these complex mixtures. In addition to the spatial resolution, chemical attribution also plays a key role here. So unlike the Amazon, where methane emissions are largely decoupled from CO and CO2, many regions in Asia showed a strong covariation between these gases, and carbon eye will leverage this covariation to differentiate emission sources and thereby improve our understanding of methane and carbon fluxes in general in highly industrialized and agricultural areas. As I show here, these covariations in here. If we move back from the global fluxes and just look at the hotspot detections, which feed into our global inversions, because that's our way to decouple them in the inversion system from wide area fluxes, we can move into the hotspot detection. This is basically localized emissions occurring at very fine spatial scales. So what I'm showing here is a large eddy simulation of a methane plume from about a 200 kilograms per hour emission source. The entire domain here only spans 900 by 900 meters. Simulation is done at 5-meter resolution. And in this case here, it means that most current satellites would have like less than a detector, but less than one footprint for this entire scene if it is a dedicated greenhouse gas mission. So this is undetectable by a satellite like OCO2 or Tropomi. With carbon eye, however, we can resolve such emissions with high precision. If we move into a target mode resolution of 35 to 50 meters, we can detect these sources with over 6 sigma confidence. What I'm showing here is the signal above the noise, so basically the enhancements over the single measurement precision. And even in global mode at 300-meter resolution, many of these sources remain detectable, though with lower sensitivity compared to the target mode. And there's a natural trade-off in detection limits between these modes. At coarser resolutions, emissions from localized sources become more diffuse, like in the coffee cup, making detection more challenging. However, carbon eye's precision remains high. To put this into perspective, in global mode, carbon eye can detect a pure methane layer as thin as 42 microns, which is a thin hair. And in target mode, it can still detect a layer as thin as 150 microns. It's a little bit higher here, the precision, because we don't co-add detector pixels. But this level of sensitivity ensures that even small, spatially refined methane sources can be observed from space, providing a major advantage over existing satellite. There was a question on Menti about like detection limits overall. In the target mode, we can go down to like 50 to 60 kilograms per hour. That's our rough estimate. It depends a little bit on albedos and wind speeds. And in the global mode, we should be able to get down to 100 kilograms per hour for methane at typical scenes. But I want to move back to the aerosols and the advantage of using the 2-micron band. So what you see here is similar to the Palisades fire example from the first slide, but this time we are looking at an agricultural fire in the Amazon. While this here may seem small compared to typical field sizes in the US and Europe, the entire scene here spans 100 kilometers, so it's larger than it seems. This fire is huge, this plume is huge, which is a large fire in the top right and numerous smaller agricultural fires scattered across the lower portion of the image. These small fires really dominate a lot of the carbon balance in the tropics, but they are hard to observe and quantify in terms of their emissions. In the visible spectrum, we basically see a thick smoke plume, but when we switch into the 2.2 micron range, the picture changes dramatically. This is the wavelength range that CarbonEye will ultimately observe. So at 2.2 micron, the atmosphere is largely transparent, allowing us to see through the smoke while simultaneously detecting thermal emissions from the fire itself, which is great because this is a dual capability. We see both the fire's thermal signature and the surrounding trace gases, and that's a major advantage of the 2-micron spectral range. And by measuring in this window, we can both pinpoint fire locations with high confidence as fires appear as bright thermal hotspots in our measurements. And we can also quantify trace gases such as CO, methane, and CO2 that are all co-emitted and are right next to the plume, providing valuable insight into fire-driven emissions, where we can better constrain emission ratios for incomplete combustion processes. And this ability to simultaneously track both thermal activity and gas concentrations makes CarbonEye quite powerful for studying biomass burning and its impact on atmospheric composition. Last but not least, on the science side, I want to highlight a few additional opportunities for CarbonEye beyond its primary focus on carbon-bearing gases. While these applications are not really part of our core mission, the data we provide will enable valuable investigations in other areas. So one such opportunity lies in land surface mapping. Since CarbonEye must disentangle atmospheric signals from surface features, we can do it also the other way around, because we operate at a higher spectral resolution than typical land surface imagers. And this enhanced capability really allows us to also better separate surface properties from atmospheric effects. So we can flip the equation around, basically. For example, on the left here, certain minerals exhibit distinct absorption features in a 2.2 micron range. And with CarbonEye's finer spectral resolution, we could differentiate a lot of these minerals much more effectively than with conventional sensors that have resolutions of only 5 to 10 nanometers. Beyond minerals, vegetation parameters can also be studied using CarbonEye's spectral range. So the right-hand side here on the far right shows the spectral range of CarbonEye, and it highlights that there's multiple signatures from lignin, cellulose, or non-photosynthetic pigments and other vegetation components. And these features provide valuable insights into agriculture, forest health monitoring, and water content analysis in canopies. Additionally, although I really don't have time to go into detail here, we also enable precise water vapor retrievals as well as water isotope measurements, offering new insights into water cycling and hydrological processes. I should mention that we have to retrieve all of these things at the same time to avoid any covariations in our CO2 and CO retrieval. So in principle, it almost comes at no cost, but we will provide the data, of course, to the scientific community. Now, moving back from our whole science and moving into something that we are very excited about, to share our first results from our CarbonEye testbed, which is basically a prototype instrument developed at JPL. And this testbed serves as a proof of concept. It demonstrates a fully functioning imaging spectrometer operating under the vacuum and temperature conditions expected for CarbonEye. And for us, it's really a critical step in mitigating technical risks as we move forward. And because technical and management and cost risks are the main decision factor for the step 2, this is really crucial to us. So what makes this achievement, though, even more impressive for me, had really nothing to do with that, is the aggressive timeline. So the majority of the work took place between October and February. And the team leveraged additive manufacturing, including 3D printed metal components, to accelerate development and iteration, really enabling the rapid prototyping. And we want to acknowledge the incredible effort for the team who pushed forward, unshackled from bureaucracy, to basically build and showcase this prototype instrument. And a special congrats also to Christine Bradley, our optical lead, who won the Best Paper Award at IEEE for her work on carbon eye design. And this paper will be publicly available soon, and we will be looking forward to sharing it with the community. Just to get like an inside look into the instrument, it's a Dyson spectrometer, and we just highlight like three key technologies that are critical to the success. One is the detector. It features an exceptionally wide format of about 3,000 spatials versus 500 spectral pixels. And this large detector size really enables carbon eye to achieve the wide swath and high spatial resolution simultaneously. Another one is the key slit design. JPL has extensive experience in that, designing custom slits, including curved slits, so that we have no keystone or smile distortion on the detector to perfectly separate spatial and spectral dimensions. And as a Dyson spectrometer, the system includes a large Dyson lens, which was also specifically prototyped and built for this testbed according to carbon eye design parameters. And the grading was designed and fabricated in-house at JPL, as well, achieving very high efficiency. Overall, these design results in one of the highest throughputs of any comparable system that enables us really to get the required SNR for carbon eye. I want to briefly flip through the remaining slides in the interest of time, but we are happy that earlier this year we had first light. In the back, you see basically the screen there showing the FPA readout live. And we were very excited to take some measurements also of gases that are in these gas cells. And we already have like one first methane fit using the methane gas cell from the prototype. And here we fit, even though this was just in a warm environment with initial alignment, we can fit the methane concentrations and the spectral calibration at the same time with really good residuals at the bottom here that made us really happy and confident that we can pull this off. So we basically have an end-to-end showcasing from the photons into our detector to kind of a preliminary retrieval and calibration at the back end. Last but not least, I want to thank the team. It really takes a village, and I can't go through all these names in here in detail. There's just some photos from a Lockheed visit, our spacecraft provider at the top, and our testbed at the bottom. Many more people that we might have forgotten here might have been involved. We've lost some people on the way due to JPL fire and the firings domain there 2 times this year. So 2025 and the end of 2024 was not easy for us. Just to summarize next steps, we are in the middle of phase A. We have a concept study report that's due in mid-June. Getting into step 1 and phase A is mostly determined by science. Now it's mostly technical management and cost that is a key factor for us moving into the next phase and being chosen. We'll have a site visit probably in September, October timeframe. There we will be grilled by NASA headquarters and their team for about a day. And then we expect a decision probably towards the end of 2025. And with that, I think I'm almost in time. This is the science team on the left side, collaborators on the top, and again, an image on the bottom from a Lockheed visit. And there are many more who have contributed to our success so far. It's been exhausting, but also exhilarating and fun to work on carbon eye. And we are hopeful to winning this. Thank you so much.
Great. Thank you, Christian, and thank you, Anna. We're going to transition now to the Q&A. So there have been a number of questions that have been entered into Mentimeter and have been upvoted, and we're going to kind of try to take them on sort of at the top. So thanks for everyone who's provided questions, and feel free to add questions and upvote currently. So I guess the first 2-part question is for Anna. First is when the launch will be, and given the current political situation in the United States, does it make it less likely that carbon eye would be chosen?
Thank you, Andrew, and again, thank you everyone for joining today. For the launch, the 2 launch years that are planned for the ESC program are 2030 and 2032, and that's the timing that we're working towards at the moment. In terms of the political situation, the reality is that that's not something that we can control as a team in any way, and so we are laser focused on putting together the best phase A study and submitting the best concept study report that we can. We think the mission and the science speak for themselves. And I will just add, and Christian alluded to this a little bit, there's a large number of applications for these types of measurements, whether it be things like methane impacts on air quality, whether it's mapping and tracking of human activity, not just domestically, but internationally. And so given the broad range of applications, we're pretty confident that this mission would have a huge impact, but the political situation itself is something that we can't engage in or comment on directly. We're just focused on the report that we're putting together.
Great, thank you, Anna. So next question is a technical one for Christian on if CarbonEye can measure solar-induced fluorescence.
Just because I worked in solar-induced fluorescence, I did not want to dilute our science with yet another variable. It would have been nice, but this is a cost cut mission, and there's only so much we can do. So we can really only afford a single band in the spectrometer, and this is focusing on the 2-micron band. So we will not have a band that focuses on the 760 nanometer range to measure fluorescence.
Great. And a question for Anna on inversions. What inversion framework will we be using?
So I'll say two things. First is because this is a NASA mission, all the data will be completely and freely available. And so what we anticipate is a large community of users that will apply myriad different inversion approaches, and we will learn a lot based on the variety of approaches, the variety of estimates that we get. And I suspect that over the lifetime of the mission, we will end up using both as a team and as a community inversion approaches that we probably will not be able to guess at from here on in. In terms of what we're planning as a science team currently, there's 3 scales that we're working at, right? There's the global scale that Christian alluded to, and there the current plan is to use a geoschem-based Kalman filter that would allow us to go down to about a 12-kilometer resolution at the global scale. Then for the regional scale inversion, we're planning to use a particle filter, a particle dispersion model, so like a STILT or high split that some of you may be familiar with. But there are now machine learning emulators for these particle tracking models that make them much more efficient to run. And so with that approach, we are planning to go down to about a 1 to 3 kilometer resolution for the regional scale inversions. And then finally, for the point sources, we're looking at a variety of different approaches that have been developed both by the science team and the broader community that would allow us to quantify these point source emissions that are relatively large and lead to larger enhancements at the local level. But again, I want to emphasize that's what we're planning currently as a science team. But as with other missions, we expect that as a result of the community getting their hands on these data, a lot of really creative solutions will come into play that will go far beyond what we as a team are doing internally.
Great. And the next question is for both of you. Can you please talk about how CarbonEye complements data from other instruments?
Do you want to go first, Christian, then I'll jump in?
Yeah, I think we really designed it to be ideally complementary because a lot of the other missions are focusing more on the global scale picture for global scale inversions, but they have really hardly any data in the tropics. So we basically kind of fill in this gap where we have this undiscovered country in the tropics that can still be used for global inversions where we can use other data sets as well. So I would say within the tropics, we are very much a lot better than any other mission. But outside the tropics, this fine spatial resolution with reduced revisits has, of course, some penalty to that. So we see that as an ideal trade-off because the other missions that might have more frequent revisit time but also spatial resolution don't measure the tropics, but outside the tropics, they're probably doing a fine job. And in my view, I see this as ideally complementary because we are really filling this gap that is existing in the entire program of record. But together with the program of record, we can really provide a much better estimate of what's going on globally, not just in the tropics. That said, we are a global mission. We want to run global inversions, and we will use in our inversion system other satellites that are flying at that time if available.
And maybe I'll just add to what Christian said, another key piece is having multiple gases coming from the same instrument, which will be really key. So having methane, CO2, and carbon monoxide all coming from the same emission will be really critical. On the coverage side, I want to emphasize this a little bit more. Even if you look at the global mappers that currently exist, they are either at really very coarse resolution, or in the case of missions like OCO2, OCO3, they have a finer resolution, but because of that, the swath width is so narrow that even after a full repeat cycle, you're not actually getting the possibility for full coverage. And so carbon has a sweet spot that you really are getting full coverage at each repeat cycle, which is not something that we have from any of the existing missions. In addition to what Christian was saying, that in the tropics, because of this fine spatial resolution, we're actually able to get successful retrievals, whereas other missions were not. And then the last thing I want to mention is this complementarity between being able to both do the global and the regional and point sources in a way that's fully seamlessly integrated within a single mission. It gets away from this contrast that I was showing early on of the global mappers versus the point imagers. It's really offering both within a single mission.
Great. And let's keep going. We got lots of questions here. So here's a question for Christian. Are you planning to consider 3D cloud effects in regions of dense cumulus clouds like the Amazon, even if you think your footprint is small enough, this would complicate things?
This is a good point. So if we had no metrics or no capabilities of accounting for scattering effects at all, this would be a problem. But the way we are tackling this is basically we have to have the spatial resolution to basically see through clouds, but also have the retrievals that are in place to basically mitigate some of the 3D effects. And we do this by using an N2O proxy gas that we will employ for variations across larger spatial domains, where the impact of scattering in general in the atmosphere, as well as 3D effects, are kind of exactly the same as the photons that we use for the methane and CO2 retrievals. So a lot of these kind of scattering effects overall, as well as the 3D effects, should cancel out much better in a single band approach, where we have the gas that we reference to in the same spectral band compared to something where the O2 band is used, where the 3D effects on photons in a very different wavelength range will be very different and can thus not be easily used to correct for these effects. So yes, we have to account for scattering impacts and 3D effects. And this is how we will work on that. There's a paper in under review for that specific aspect.
Andrew, I got a note that some people might still want to be able to see the Mentimeter. So I'll share my screen again just for a minute so that folks can log in if they're not currently in Mentimeter. But we can keep answering questions while that's up.
Absolutely. So the next question is, excuse me, for you, Anna, on could you please re-explain the counterintuitive notion that measuring less frequently at fine resolution results in shorter effective revisit times?
Sure. So this is something that Christian explained, and he might want to chime in as well. But think of it this way. Think of a location, like some of the locations that Christian showed, where you have this persistent fine scale popcorn clouds. Even if you could revisit that location every day or even at sub-daily scale, because of that cloud contamination within a single large pixel, you would never actually have a successful measurement at that location. If you go to the other extreme, where you would have an extremely fine observational footprint, you could always find spots between those clouds where you could make measurements. But then the trade-off would be that if you want to have full coverage, your repeat time to get back to the same location would be incredibly long. And so the sweet spot that Carbon is aiming for is, and this is what Christian led a paper about last year, is what is that spatial observational footprint, so that if you look at what is the probability at a given location of finding a fully cloud-free pixel, and how often will you return to that same place? The effective return time then is the time between successful observations rather than just simply the time that the instrument happens to be in the same place again. And so that effective return time is, how do you optimize, how do you make the time between successful observations as short as possible? And this is what we use to select the spatial footprint for Carbon Eye, and then that's what dictated some of the downstream design choices that Christian talked about as well.
Great.
Thanks. I have nothing to add.
Great. So we're sort of getting close to the top of the hour, but I think we can do at least one more question. So this is for Christian. How quickly would mission control be able to switch Carbon Eye from global mode into target mode? For example, if there was a fire that broke out in Los Angeles, how many days would it take Carbon Eye to observe it in target mode?
This is a great question. Let's take one step back and just have the overall design of the target mode. So we calculated that if we want to revisit something like every 7 days, we actually can use orbits that are relatively close to the location that we want to look at, so that we can see them within angles of about 30 degrees of nadir pointing. So that will make it relatively easy. With that, we could observe everything like about every 7 days. But if something specific happens, like what you mentioned here, we can probably revisit it in about 1 to 2 days. With a caveat that we have to look pretty much off angle. So the pixel sizes will get a little larger, but we calculated if we can relax that requirement to 50 to 60 degrees, our potential revisit time is on the order of 1 to 2 days. It depends on a little bit on luck, like when the next orbit passes over that location, so that we can actually point off nadir to observe it. But it's on the order of less than 2 days typically if there's really a special event. We want to have this as an exception and not the rule, because it would be quite rather costly to do it on a regular basis. But yes, if something big like these fires happen, or something like Nord Stream 2 pipeline, these are the things that we want to be able to observe as kind of a rapid response. And with rapid, we mean 1 or 2 days.
Great. So I think we're going to end things here. Thanks everyone for all of the great questions. I want to thank our two speakers, Christian Frankenberg and Anna Mikulak, for the presentations. And on behalf of the Carbon Eye team, thanks everyone for joining. We plan to have more of these webinars in the future. We just haven't determined exactly when the next one will be. So with that, thanks everyone, and have a great rest of your day.